Hey everyone. I'm going to try to make some screencasts again since I'm not in class to kind of refresh what we've talked about. Looking at your guys' reflections, it seems like there's still some confusion on the learning targets, so we'll just kind of go back over those learning targets before the test here just to kind of refresh and review for some of you, especially if you ended up missing some of those notes that we might have taken. So I'll start with the first one, learning target number 1. And so this is interpreting the components of a chemical equation or a chemical reaction. And really what this comes down to is just when you look at a chemical equation, just understanding what all those different parts mean. The first couple I think are pretty straightforward, and the last two parts of that are maybe a little more confusing. So we'll just kind of start with this first one. And one thing you should know right off the bat is part of this first notes that we looked at came from a interview I had a few years ago, and it was actually for a chemistry position. And little did I know then that I kind of messed some things up. So people that interviewed me probably knew right then and there that I wouldn't be good for chemistry that year, because they could probably pick out right away some problems with what I had in here. And one of the problems is this equation. So FeO2, the product, is not really, I'm pretty sure that's not really um, a real product for iron and oxygen. You got two others that are more common, and FeO2 is probably not one of them. So anyway, let's start with the first one, reactants and products. I think most people hopefully have that down. Typically when you see a chemical reaction or a chemical equation, you'll see it written like this with the arrow pointing to the right. And so your reactants are going to be on the left-hand side, and your products are going to be on the right-hand side. And so, like the name says, reactants, those are the things that are going to react together. And then, of course, the product is what you're producing. Sometimes you'll hear another name for reactants. You'll hear that called reagent. Same thing. Again, there's a lot of synonyms for the things that you'll read, so you might come across a slightly different name sometimes, but a lot of times that means the same thing. So reactants or reagents, same thing. And then again, products is what we're trying to make. And of course, what we're making is something different than what we started with. That's the whole idea behind a chemical reaction, or a chemical change, as compared to a physical change. And that's, again, is where we're not actually changing the chemistry of the thing. So examples of physical would be boiling water. Turning it from a liquid to a gas. It's still water, so that's not a chemical change, it's a physical change. So with that said, again, we've got reactants versus products. The other thing on the list was states of matter, and you'll kind of see that below. So again, if we're changing from one state to another state, that's a physical change. But in a chemical equation, a lot of times you'll see these symbols. About half the time I'd say. Sometimes you won't see them at all, but sometimes you'll see them, because it would be nice to know sometimes, hey, is my product going to be a gas? Because if it is a gas, and I just have it just kind of sitting out in the open, well, that gas is just going to, of course, move into the atmosphere and kind of dissipate. But if I want to collect a gas, I need to kind of be prepared to try to set up that reaction so that I can capture that gas. So it's just nice to know. It's just extra information. And the first three, a lot of people have probably heard: solids, liquids, gases. The fourth is the one that may be new to some people, and that's AQ, again, for aqueous. And what that means, you can see it in the slide here. It just means that we have something that's dissolved in water. So a lot of times in labs this year, you guys saw copper sulfate. That was that blue looking liquid. Some people thought it looked like mouthwash. And that's an example of an aqueous solution. And so in that sense, we have a couple ions, a copper ion and a sulfate ion, and they're dissolved in water. So anyway, that's just, again, information to kind of know when you're looking at a chemical reaction. The other two, like I said, that are a little more confusing are, and I'm going to start with the fourth one, Hofbrinkel, I think most people have this down now, but you know, sometimes it's just easy to forget. And again, if you got a chemical reaction, especially where you're going to be writing a chemical reaction from words into formula, it's easy to forget sometimes when you have these elements and these elements are on their own. You got to remember, okay, it's not just oxygen, and I'm going to change that into O. It's going to be oxygen, and that's going to turn into O2. And all these are covalent. So remember, if you do those Lewis dot diagrams, you can actually see why these actually bond with each other, because it just works out that when you have, for example, two iodine atoms, you know, like those puzzle pieces, they're actually going to share two electrons, so they're going to bond covalently. And that kind of makes sense in terms of electronegativity, because if you have two iodine atoms, neither one wants any electrons more than the other. And that's really the key to ionic compounds, is that you have one element that really wants electrons more than the other element, and so you get a transfer of electrons, and that transfer of electrons creates ions. But in the case of covalent, especially with these seven you know, elements here, there's no difference in electronegativity. So again, one fluorine doesn't want any electrons more than another fluorine does, and so you get covalent bonding where they're sharing two electrons. And again, you can see that when they share those two electrons, each fluorine atom is going to have 8 electrons total around it. Same with the others, with the exception for hydrogen. Hydrogen, of course, will only have 2 electrons around each atom, because that's closest to helium, and helium only has 2 electrons around it. So anyway, what's kind of confusing about this, I think, the one mistake I see some people make sometimes, if they happen to remember Hofbrinkel, is that sometimes they'll see this, you know, these elements, of course, are in numerous other compounds. And so if, for example, you had water, H2O, you know, people might wonder, hey, why is it not H2O2? Because you just said that Hofbrinkel, there should be, you know, 2 of each. But again, this is when these elements are by themselves. And if you have water, which is H2O, hydrogen and oxygen are not by themselves. They're actually combining into something new. So again, this Hofbrinkel is just for these 7 elements when they're by themselves. And you just got to remember, again, hey, do I have any of these elements in this equation? And if so, and if they're by themselves, then you got to remember that they're diatomic. You get 2 of them, so it's again H2O2, F2, and so on. So the last one, which I think I probably could have spent a little more time on, is the counting of atoms. You know, based on the last couple quizzes we've taken, some people are missing that question still. And again, I'm trying to really throw everything at you that I can to make sure that you really understand counting atoms. So we have a few different things we're looking at when we're counting atoms. And, you know, just looking up some things on YouTube, one that I came across, you know, kind of starts to explain that. But I'll kind of first look at the example I gave you guys in class, which was the formation of water. This is what you guys saw in class when we had the 2 gases. So again, we had H2 for hydrogen, we had O2 for oxygen, and we went ahead and ignited those. So this is a picture that Liam took on his phone, which is pretty awesome. So that's what you're seeing there. And again, when this reaction is happening, you're actually forming water. Of course, it's not going to be so much water that we could drink it or throw it on somebody and or whatnot. But again, a tiny amount of water coming from those gases. So let's see what else. We were going to look at these again real quick. So one of the things you see is we have these subscripts, of course, 2, which means, of course, again, we have Hofbrinkel here, hydrogen by itself, oxygen by itself. And we have 2 hydrogens and 2 oxygens, and you can see that down here in the picture, 2 of each. And then sometimes, you know, you'll have this coefficient. And so that's another number we need to take into consideration when we're doing when we're counting atoms, because now you can see in the pictures and here as well, if we had a hydrogen molecule, 2 hydrogen atoms, but now we have 2 of those, well, now we have a total of 4 hydrogen atoms, because 2 times 2 is 4. And again, you can see that down here, 2, 1, 2, 3, 4. And so again, those two maybe are a little straightforward. What's a little trickier is when you get something like this. And again, I just kind of quickly saw what was online. You're going to find when you look for things like this, there's actually an overwhelming amount of information. It's kind of the hardest thing, I guess, is trying to figure out which ones make the most sense, which ones are the shortest. But this one kind of goes through the other tricky aspect of this, and that's when you have parentheses involved, and that's going to when you're going to have polyatomic. So you can see here we've got the same thing, the subscripts, the coefficients, but now we've got this as well, which kind of identifies that we have 2 sulfate ions. And so this, I'll just kind of play this briefly. It's LPS chemistry. 3.2 number of atoms. This is probably one of these channels where they've got lessons after lessons here. But I'll just kind of let this play for a second to explain that last bit. That's giving some people trouble, I think.
Now, if we look at the next compound in this equation, we see a little bit, it's a little bit more complicated. We see that we have these parentheses around this SO4. So let's figure out first that we know there are 3 different types of elements in this compound. We have Na, or sodium, S, for sulfur, and O for oxygen. Now, the first thing that I'm going to do is whenever we see the parentheses and a subscript outside that parentheses, which is 2, we want to distribute that subscript into both elements in the parentheses. So we see that this 2 multiplied by that 4 is going to give us 8, and that 2 multiplied by that 1 is going to give us 2 for sulfur. However, we also have to remember that there's a coefficient of 2 in front of this entire compound, which applies to every element that we see, including the ones in the parentheses. So we're going to take this 2, the coefficient, and multiply it by our new subscript of 2 for sulfur to get a total of 4 sulfur atoms. And we want to take this coefficient of 2 and multiply it by our subscript of 8 to get 16 total oxygen atoms. And then lastly for Na, we want to take this 2 coefficient and multiply it by the subscript of 2 that is currently on Na. And 2 times 2 would give us 4 sodium atoms.
So that kind of maybe explains a little better than I have what's going on, especially when you have the parentheses. But the bottom line, again, for this learning target is just really understanding all these parts in a chemical equation. We're not even balancing it. We're just really trying to make sense of what all this stuff means. And so again, we want to be able to count atoms because we want to be able to conserve mass. And also, you'll see like this example on YouTube, they've got the AQ again. So when you see something like sodium sulfate, it's telling you that this is actually sodium sulfate that's been dissolved in a liquid. So you can imagine, one of these flasks filled with liquid. It might be clear, might be some funky color, but that's what you got there. So hopefully that helps some of you guys a little bit. But again, just as far as learning target 1 goes, just kind of interpreting and making sense of what is in a chemical equation. So I'll move on to learning target 2.